All right. Now we're going to be looking at question 2 on the 2026 AP Physics 1 exam. And so here we have two small disks, R and S, on a horizontal track. At time t equals 0, disk R, mass m naught, is located at position x equals 0, and disk R is initially moving to its speed v naught in a positive x direction. Disk S, which has a mass of 3 m naught, is initially not moving, as shown in figure 1. Friction is negligible. Perfect. Okay. This looks like a momentum scenario. At time t equals t1, disks collide. Yep. And then immediately after the collision, disk R moves at the speed half v naught in the negative x direction. So half the amount of momentum to the left. Okay. The momentum vector diagram in figure 2 represents the momentums of R and S before the collision. So R has 4 units of momentum to the right, and that is actually equal to m naught v naught. And then disk S has no momentum, and we are asked to draw arrows on figure 3 to represent the momentum vectors of R and S after the collision. Okay, perfect. So disk R is, after the collision, going to be moving to the left at half its original speed, so it should have half the amount of momentum to the left. So we'll draw an arrow that is 2 units, which is half of 4 units to the left. And because of that, disk S should have a momentum to the right that allows for the momentum to be conserved. So since we have to have a net 4 units of arrow to the right, and we already have 2 to the left, that means that disk S should have an arrow that is 6 units long to the right in order for the momentum to be conserved. Perfect. That should do it. Okay. Part B. Starting with conservation of linear momentum, derive an expression for the kinetic energy of disk S immediately after the collision in terms of m naught, v naught, and physical constants. All right. So we'll start with conservation of momentum. So that means the momentum, or the mass of S times the initial velocity of S plus the mass of R. Actually have that switched, so let's turn that around. So the mass of R times the initial velocity of R plus the mass of S times the initial velocity of S should equal the mass of R times the final velocity of R plus the mass of S times the final velocity of S. And these are all vectors. If we actually start substituting, this is, I believe, is m naught times v naught plus 0, since S is not moving to begin with, should equal m naught times negative v naught over 2 plus 3m naught, since S is 3 times as large, times its final velocity. So we can cancel out our m naughts. And that gets us v naught is equal to negative v naught over 2 plus 3 vf. So that should give us 1.5 v naught is equal to 3 vf. So that final velocity for disk S should be positive v naught over 2. So it'll be going the same speed, just in the positive x direction instead. We were asked to find the kinetic energy of disk S, however, so that should equal 1/2 mv squared, which is 1/2 times 3m naught times v naught over 2 squared. And if we clean that up a little bit, I think that is 3m naught v naught squared over 1/4 times 1/2, which is 1/8. It should be the kinetic energy for S. Perfect. All right. I think that answers part B. Okay. Part C. The graph shown in figure 4 represents the positions x as a function of time t from t equals 0 until t1 for disk R, S, in the center of mass of the 2-disk system. Okay, so 3 different graphs here. On the graph shown in figure 4, draw 3 lines that represent the positions x of disk R, S, and the center of mass from the collision to a time after the collision, and then we'll have to label each line. Okay, perfect. So it seems like R goes from moving with v naught to the right to negative v naught over 2, or speed v naught over 2 to the left, and then just S goes from not moving to moving with a positive v naught over 2 to the right. So let's try and graph that on figure 4. Okay, so disk R, we know, is going to be going half as fast. So it seems like the slope here happens to be 2 units up and 1 unit to the right. So we'll draw a line for R going with a negative velocity that is half the value of that initial positive velocity. So that should be disk R, rebounding at half the speed. Disk S should be going up at that same speed, or forward at that same speed rather. So increasing positive x values at the same rate. That should be disk S. And then because this is an isolated collision, center of mass should actually be going at the same speed. There are no external forces acting on the two objects. So no external forces means a constant center of mass velocity. So it should just continue at the exact same speed. And that should do it for that graph. Perfect. All right, on to part D. During the collision, the magnitudes of the changes in momentum of R and S are delta PR and delta PS respectively. Indicate whether delta PR is greater, less than, or equal to delta PS. All right, let's do that. So because it's an isolated collision, they should actually be the same. So delta PR, it's probably at least two ways I could think of how you could argue this, probably more. So first we can do the conservation of momentum idea. So due to conservation of momentum, the change in momentum of R plus the change in momentum of S has to equal zero because this is an isolated collision. And if that's the case, then um, then it shows that delta PR in terms of vector form should be the negative of delta PS. So their magnitude should equal. Perfect. That should work. Another way to sort of justify this, I think you could argue using Newton's third law. So we could say because of Newton's third law, the force of R on S is equal to the negative value of the force of S on R. And therefore, the magnitude of the force times the time should equal the magnitude of the force times the time, since they'll have the same amount of time in contact with each other. Therefore, the change in momentum of S should equal the change in momentum magnitude-wise of R, since it'll be the same force in the same time, so the same impulse.